Hey guys, welcome back to another video. Today we're going to be looking at linked lists, why we use them, how they work, and also we're going to be coding one in Java. Alright, so what's a linked list? A linked list is a linear data structure that's used to store a collection of elements. So it's similar to like an array. So let's draw an array here and let's give it some boxes to represent the slots in the array. And we got indexes 0, 1, 2, 3, 4, 5. In the actual memory of your computer, when you make an array, all the items are stored next to each other. So let's put in A, B, C, D, E, F. In the actual memory of your computer, they're all stored next to each other, but a linked list on the other hand is very different. Let's draw a linked list so you get an idea. If you haven't seen linked lists before, they look something like this, where it's a bunch of nodes. That's what these are called, these circles. And they all kind of point to each other. So we could do A, B, C, and it's a similar idea where we have A and the next one is B, then C, then D, whatever. Here we have a node pointing to the next node, which points to the next node, and then the last one will point to null. But what are these nodes? A node is a simple object that stores two values: the data inside, which in this case would be the letters, and the reference to the next value. So in this case, the data here would be A, and the next value would be this arrow right here pointing to the next thing. In Java, this arrow here would be a reference, but in other languages like C or C++, this would be a pointer. But it's basically the same thing for our use case. So you might be asking now, why would we even use a linked list when we have arrays and you can instantly take out and put in new items? Well, first of all, there's a fixed size, because if I wanted to add G to this, you can't do this. This is not allowed. Instead, you would have to create a whole new list and add all the things in one by one and then add the next item. And this is really slow. This is actually, in time complexity, it's O of n. N being the number of items in the list, we have to go through every single one. While in our linked list here, if we wanted to add D, you can just redirect this arrow to point to a new node that you create and call it D. And this would be O of 1, being the fastest that you can actually do something. Additionally, it's really slow in array when you have to insert or delete. Like we just covered, inserting at the end would be expensive, or anywhere else if it was full, because you'd have to create a new array. And similarly, if you had to delete something, like let's delete D, you would have to create another array with a smaller size and then just put everything else except for D in. And this is really slow too. However, linked lists also have some drawbacks to them, as each one of these nodes contains these two values, which actually takes up more space than using an array. And it's actually really slow if you want to get like B, for example. If you want to get B here, it would be pretty fast. It would be O of 1 if you already knew where it is. And if you didn't know where it was, if this was sorted, then it would be O log n if you did a binary search or a really fast search algorithm. But you can't do any sorting algorithms on these linked lists because you don't have any indexes to go to. You have to start at the front or the end, and then you have to just go one by one until you find the thing you're looking for. So if B was at the end of the list right now and we started at the front, that would be O of n, which is slow. The next thing I want to talk about is that there's three types of linked lists. There's the singular linked list, the double linked list, and the circular linked list. And now obviously you could have more if you just made more, but these are the main ones. The singular one is like the one we have right here, where we have one node that just points to the next and just points to the next, and then at the end it just points to null to show that we're at the end of the list. The second type is a double linked list, where it's similar to the other one, where we have something like this, but we also have pointers going back or references going backwards. Now obviously null can't point backwards, it's not something. So if we were at this node, we could go backwards and then we can go like forward again, and it goes back and forth. And a circular linked list is a bit different. So if we had three things, we could go this way, and then this way, and then it goes in a circle like this. Now remember that node I was showing you? This is a class representation of what we would code in Java if we want to make a node. We would just make a class, which is an object, and inside we would store int data, but this could actually just be any type that you want to store. But you especially need this next node. That's how we get the reference to our next node, and we go from one to the next. And this is just a constructor right here that makes it easier to make the object. Now you'd want to take this node class and create a node head in your linked list class. This is the class that you're actually going to create an object for when you want to make a list of something. And if you want it to be even faster, you would actually also create a node tail. The reason why you would want a tail on your linked list is because let's say we have A and B right here, and you want to add C at the end of the list. If we only have head, we would start at A, then we would go to B, then we would make a new one C, and point this one to there. But we would have to go through A and B to do that. While if we just had tail right here, if we had that, then we could just start at B, and then we could just add C at the end, with A already being there, of course. So you wouldn't even have to go through A, you would just already have B, and that would make it instant, or O of 1 I mean. Here's a simple add method that you can use if you want to add something to your linked list. So for a parameter right here, we're going to have int data, but this is going to be whatever type you want to add, of course. And then we're going to create a new node with that data because we're going to have to add a node. Then we check if the head is null. So let's try this out. Let's do add 1 or something, and let's go through it. Right now we have nothing here. So we create a new node with 1 in it, and then we check if the head is null. Well, head is currently null, we haven't set it to anything. So we just go in here, and then we set the head to the tail to the new node. So now we're going to make the head equal to this and the tail also equal to this. And then we just return and we don't run the next lines of code. Now let's add 2. So let's run add 2. Now of course you don't have to go in order or anything. That's just the way I want to do it. Now you create a new node 2, but it's not connected right now. Then we check if the head is null. Well, head is pointing to 1. 1 exists. It's not null. So we're going to skip this and we're going to go over to the next line, which is tail.next equals new node. Now, where's tail? It's pointing to 1, and its next isn't pointing to anything. There's no arrow coming out of it. But right here, we're not getting that arrow. We're actually setting it. Tail.next. This is tail, and we're going to set its .next point to the new node, which is 2. And then we set tail equal to the new nodes. So this right here, this tail is no longer going to be pointing to 1, it's going to be pointing to 2. Head, it will still be 1 because that's the front of the list. And now you could keep going as you add more things. Also, this is really great because this is actually O of 1 time complexity, which is instant. And if you want to add to an array, if you want to add to an array and you had to resize every single time, that would be O of n. By the way guys, quick note, this is the time complexity chart where on our y-axis we have computations, or like the amount of stuff we have to do, and on our x-axis we have like the number of n, the size of n, or n number of nodes. And as you guys can see, O of 1 is really fast because it has the lowest y value right here, but log n is a little bit slower, but it's pretty good, while n, as you guys can see, is linear. This is pretty slow compared to our O of 1, which is the fastest we can do. Now obviously when you guys are writing algorithms and stuff, try to avoid these ones right here because they're really slow. You want to stick to these because these are the fastest you can do. Alright guys, now we're going to work on our delete method. You guys can follow along as I try to show you guys how to do this. Let's say we want to delete 1 right here. We're going to see if the head is null. Well, the head is 1, is not null, so we're going to skip that. Then we're going to check if the node to delete is the head. Well, are we trying to delete the head? Well, the head is 1, we're trying to delete 1, so yes. So let's check. What we have to do is we have to set the head equal to the head.next. So the head, which is this right now, we're going to set this to this .next, which is 2. So now this is head, and this, oh my god, and this no longer exists because nothing's pointing to it. It gets collected by the Java garbage collector. Then if the list is empty, we just reset everything back to null, but it's not empty. We still got 3 things here, so we just return true and we do nothing else. Alright guys, let's do a delete on 4 next. So if we wanted to delete 4, we would have to do this first, but the head is not null, so we're going to skip that. And we're going to skip this 2 because we're not looking for the head right now, which is 2. So we're going to skip that, and then we're going to do this. We're basically just going to go from one item to the next like this in a while loop. So we set current, we make a new node called current, and we set it to the head. So right now the head is 2, so we're going to set current to 2, and then current, while the current.next is not null, well, what's the current.next? Current is 2, its next is 3. Well, that's not null, so let's continue. and current.next.data is not the key. Well, current.next.data, which is 3, well, the key right now is 4, and that's not 3, so we're going to continue, or we're going to set current to its next value, which is 3, and then we're going to check. 3.next is 4, so that's not null. Continue. Current.next.data is the key, because we're looking for 4, and our current next data, which is 4, is equal to 4. So we actually fail this, and we're going to stop, and we're going to go down here. We're going to check if the current.next is null. Well, current right now is 3, its next is 4. That is not null. So we're going to skip this, and now we're going to remove the node. So current.next is 4, and that's the thing we're trying to remove. Basically, we're taking our pointer right here, we're removing that, and we're going to make it point to this is next, which is null. So we're basically just pointing to null right now, and we're skipping this. It's just going to get collected by the Java garbage collector. Then we check if we remove the last node, and if we did, then we're just going to set our new last node to 3, or the next last item. So since 4 was the last node, we're going to check current.next equals null, and since that's true, we're going to set tail to our current, which is 3, and that's our new tail, and then we're just going to return true since we were able to actually delete something. Alright guys, these are the last two methods that I'm going to go over, contains and print list. Now these are really simple, way simpler than delete. All contains does is it does that loop from before from the delete method, but a simpler version where we just start at the head. So if we have a list of 1, 2, 3, we're going to start at the head 1, and then we're going to go and use our loop to see if 2 is null. Well, it's not null, so we're going to go to 2, and we're going to check if that is the key we're looking for. So if we were looking for 3, we'd be like, that's not the key we're looking for, so we're just going to go continue next. So we go from 1, then 2, and then we go to 3. And we find 3, we see this right here, if current.data equal key. So if the current equals 3, because we got all the way to 3 from going from 1 to 3, we check if it's equal to 3, which is going to be the key, that if we were doing that example, and yeah, that would be true. So we just return true. And let's say you go through the whole list and you couldn't find it, then you just return false at the end. And similarly for print list, we do the same loop, but instead we don't have any of this in here. Instead, we just run a print, and we just print the thing that we're at, and then we go to the next thing. So we would print 1, go to 2, print 2, go to 3, print 3, and then we'd be done. And we can print null at the end or nothing, whatever you want. Alright guys, I put all those methods that we just went over into a class in Java, and now we're going to run this code with some test code in our main method, where we create the list, then we add 3 items, 10, 20, 30, and as you can see, after printing, we get 10, 20, 30, and then null. That's just the last reference. Then after deleting 20, we just get 10 and then 20, then null, and then we delete, and then we check if it contains 30 and it contains 40. 30 isn't the list, obviously, so we're going to return true. 40 isn't, so it's false. And then we add 40 and we get this as our final thing. I'm going to include this code in the description if anyone wants it, and adios.